Hello, everyone, and welcome back. We are in the MCT4C course, the Math for College Technologies, grade 12. This is Unit 4, and we are on Lesson 19 out of 20 lessons, so we're pretty close to done. And this is Class 31. So we're having a look at understanding some properties of the circle. And in addition to that, I thought it might be worthwhile for us to review some properties of angles in case you've forgotten it, as well as just general properties of and characteristics of a circle. It's worth noting today will be where the focus is on being able to identify and be able to determine missing angles. So we'll know things have gone well if we're able to turn the angle measures in lines and shapes and be able to describe and identify various properties of circles. Okay, so let's get started. So in terms of an angle review, so if you've seen this before, great. If not, we can go ahead. This will be an excellent journey of review for you. So a right angle is a geometric shape that forms a perfect corner. And so we usually describe this. So you might see two lines and you see this little box in the corner. This little box in the corner means that it's going to be a right angle and it's going to be 90 degrees. And so we end up with a consequence where angles are considered complementary when they both add up to 90 degrees. So consider the example I have here shown in this box. I have a right angle that runs as such, and we have a line that cuts this right angle to two parts, 40 and 50 degrees. And so we would say that if we were to take 40 degrees plus 50 degrees, that equals the entire corner, 90 degrees. And that's considered to be complementary. Okay. A straight line has a measure of 180 degrees. So consider just a protractor sitting on a line. And lines are considered to be supplementary when the two angles sum to 180. So here, if you have having a look at the diagram, suppose we have angle P and angle Q. If you were to adjoin these two together, P plus Q would add up to 180 in this case. So I think angle P maybe looks to be about a 40-degree angle. Q would be, say, maybe 140. And you could take 40 plus 140 degrees, and that'll give you 180 degrees as an example in this case. We've talked about this one quite a bit, but again, since we're talking about review of angles, seems a good time to bring it up. The total angle measure around the center of a circle is 360 degrees. Okay. And the interior angles of a triangle sum to 180 degrees. So if you were to add, say, A plus B plus C, those all equal 180. And so we're going to use these properties and characteristics to be able to answer some review questions here for us. Okay, so in example one, we're going to find angle measurements involving lines, circles, and triangles. And so we're going to find the value of the indicated angle in each of these diagrams. Okay, so letter A here, we have a 106-degree angle. I should also mention that if the angle is larger than 90 degrees, this is what we call an obtuse angle. If it's equal to 90 degrees, we call this a right angle. And when I say larger than 90 degrees, I mean between 90 and 180, because I'm going to bring up a different angle here. If your angle is less than 90 degrees, this is called acute. If your angle is equal to 180 degrees, we just call this a straight angle. And if your angle is between 180 and 360 degrees, we call this a reflex angle. Just some terms you may remember or may have forgotten, but this is just to make it easier when we go ahead and solve these. And so for example A, when I talk about this angle of 106 degrees, that's an obtuse angle, and we wish to know the value of x. Well, we know that 106 plus x must add up to 180. And so if I take 180 degrees, or I should say, x will be equal to 180 minus 106. So on your calculator, take 180 minus 106. You get that x is going to be equal to 74 degrees. So far, so good. What about letter B? And you might already know what the answer to this one is immediately before looking much longer, but that's okay. We're going to assume that you're not sure. So how do I solve this? Well, I notice that, and keep in mind, we've got two intersecting lines where the obtuse angle given is 133 degrees, and we want to figure out the other obtuse angle. And so if you notice here, we have two lines that just intersect at a point. But if we notice, say, this red line here, this has an angle measure of 180. So we could figure out this angle, say, theta first. And then we can use the same property to figure out what the green line should be. And so here, theta would equal 180 minus 130 to 33 degrees. So theta would be equal to 47 degrees. And again, if you're ever unsure, just go ahead and just check this using your calculator. Okay, so now that we know theta, we can figure out x. And so we could say x will be equal to 180 minus 47, which means x will be equal to 133 degrees. And we'll go ahead and box this as for our answer. Okay, so I did mention at the start that you might have been able to guess this right away. This is an example of what we call opposite angles. And opposite angles are equal. So if you have two lines that intersect and you know one side is 133, the opposite side will be 47. And so the other side will also be 133. So in our case here, when we figured out the theta had to be 47, the opposite side will also be theta and then be 47 as well. And the angle we are interested in would be 133. So if you run into this structure, just know that you can quickly figure out all the angles. All right, what about letter C here? So we have, looks like there's a right angle and two potentially obtuse angles is what it looks like, perhaps larger. So what do we do here? Well, recall that we said an angle is 360 degrees. So if you imagine we just kind of continue this all the way around, we can take 360 and minus off the 90 and the 112. So the missing angle of x would be equal to 360 degrees minus 112 minus 90 degrees. So x would be equal to what? Well, 360 minus 112 minus 90 is going to give us an angle of 158 degrees. Okay, so we're just using the fact that the circle contains 360 in order to solve this. Similarly, for letter D, we have the case where we're solving for two x's, but we're only given one angle side. Well, we know that all three of these must, at the 76 and the two x's, must sum to 360. So we can write that as a statement. So 360 degrees must be equal to 76 degrees plus x plus x. Well, x plus x is 2x, so 360 degrees is equal to 76. I'm just going to drop the degree symbol here because we don't need it for the moment, is equal to 76 plus 2x. We can subtract 76 from both sides. So 360 minus 76 is 284 is equal to 2x. And so x will be equal to half of 284. So if I take 284 divided by 2, I get that x is equal to 142 degrees. Useful property, and we're going to see this one come up again. Okay, what about letter E? So for letter E, we have these hatch marks again, and we were given that the one side we're looking for is 70 degrees. And so we know because of this hatch mark, that this angle is 70 degrees, which means this other angle will also be 70 degrees because the side is the same length there. And so we know that this will be 70 degrees. This is what we call an isosceles triangle. And the book is going to have us make use of this fact. So a characteristic of an isosceles triangle is that two of the sides are the same, as well as two of those same corresponding angles will be the same. And so we can use this fact to figure out angle B because it's still a triangle. So if we were to take 180 degrees, or I should say angle B is equal to 180 degrees minus 70 minus 70. So angle B will be equal 180 minus 140. It'll be equal to 40 degrees. Okay. Uh, letter F, what about this one? Well, we appear to have a triangle and then we have an exterior angle. There's a theorem involving the exterior angles of a triangle, but we don't need to worry about that for our course purposes. So what do we do here? Well, let's focus our efforts on this angle here first, because this is a straight line. And if we were able to figure out an additional angle inside of the triangle, we could just use the fact that a triangle's angles sum up to 180. Consequently, we should figure out this angle theta first, because theta is on a straight line. So theta will be equal to 180 minus 113. So 180 minus 113 is going to be 67 degrees. And then angle X will be equal to 180 minus 67 degrees minus 85. So if I take 180 minus 67 degrees minus 85, I get 28. Okay, and that'll be our answer. So sometimes we need to do multiple steps, sometimes we need to do one step. Okay, two more examples, and this is kind of where we wanted to go with this. The point of what we were doing for the review is to actually do this kind of calculation. So now we have circles with triangles inside of them. So this is what we are curious about. So here we have a circle, and inside of it, we have angles C and B that we are interested in. So how do we do this one? Well, remember, for a circle here, if we have the center of the circle that extends to an outside, that's the radius r, and we can see we have two of them. So we have two r's inside of the circle. Well, and the reason why I put r is because we don't really know how long that length is. It could be 3 kilometers, 4 kilometers, 2 inches, 2 millimeters. We don't know. But what we do know is that the r's are the same. So consequently, this will be an isosceles triangle. And this was the key point in order to solve this kind of question, because we now know what angle B is going to be. B is just going to be 21 degrees, because it's the exact same question as question letter E, because those angles are the same. And so angle C will be equal to 180 minus 21 minus 21. So angle C will be equal to, and I think I can shrink this down a bit perhaps. There we go. C will be equal to 138 degrees. Okay, lastly, but not leastly of the angle examples, we have letter H here. And so we formed another line inside this triangle. So we now have a diameter and a radius, as well as an unknown term. We don't know what to call that yet, but we're going to learn shortly. So how do we solve this? Well, it seems like we might want to figure out, and I'll highlight this in red, feels like we might want to be working with this line first and determine the angle inside of this triangle, that obtuse angle. So let's call this angle something clever, perhaps theta. And we can then use the fact that we have two radiuses here, and it's another isosceles triangle. Okay. So theta will be equal to 180 minus 58. So theta is going to be equal to 122 degrees. Okay. Now, with that in mind, we know that there's an angle H, but we know that the angle H will be the same for both of them. So H will be equal to, oh, not H. I should mention that the interior angles of a triangle will sum to 180. So the 180 degrees will be equal to theta, which is 122, plus H plus H, because there's two angle H's. So this will be 180 is equal to 122 plus 2H. Minusing off 122 gives us 58 degrees will be equal to 2H. And half of 58 is 39. Okay. And if you're ever unsure of your answer, you can always just type this in to make sure that things have gone according to plan. Oh, they did not go according to plan. So I should mention that half of 58 is in fact 29. So let's try this one again. 29 plus 29 plus 122. Yeah, that's 180. So H is going to be 29 degrees. And so these were the two examples that'll help you with a couple of the key questions in the lesson, namely G and H. But to get to G and H, I wanted to make sure we had knowledge of these previous ones. It's also useful to talk about angle notation. So you can see from above, we loosely said angle C or angle B, which much more common is that we have a fully labeled diagram. So we need to be able to understand and read angles. Sometimes there can be ambiguity with respect to circle diagrams. Consequently, we need ways to differentiate the angles under study. The following circles shown below is a circle with several intersecting lines. And so we're just going to intersect this. So here we've got, well, we've got quite a lot going on. We've got, looks like a quadrilateral, A, B, E, D, and then we have point C that seems to create two more quadrilaterals in here, kind of this strange looking, I'm not sure what you would call that. I just look at this and I see like the Star Trek, their Star Trek badge. This one kind of reminds me of that, as well as, but in general, they're both quadrilaterals. And so we need to be able to distinguish what we're talking about. And all we're going to do is just here is we want to talk about what each of these angles are. So here, if I want angle ABC, this would be ABC. That's going to be 31. What about BED? So BED, that appears to be 126. What about BAD? That appears to be 56. EDC, EDC, that looks like it's going to be this one. That's going to be 68. What about CDA? CDA, that one appears to be 25. And what about EBA? EBA, ooh, trickier one. So if you notice, EBA happens to be this entire thing. So we got to add together that 31 and 54. So 31 plus 54, and perhaps I should label this below, that angle EBA is equal to 31 plus 54. So angle EBA is equal to 85. So I'm just showing that calculation below how we come up with this. And here's an ambiguity. So if we have a look, and I'll label this in green, at DCB. So here, the way that the book will differentiate this is they'll say the obtuse angle. And you might be thinking, obtuse angle? What do you mean? Oh, you mean the thing that's between 90 and 180? Yes, that's how they'll differentiate these. So the obtuse angle DCB will be 112, but the reflex angle is the other side of it, because that you can describe it the same way. So DCB would be 248. Okay. And so that's how we can end up with some ambiguity in these, insofar as we need an effective way to describe this. And this is how they differentiate those. So so you might end up with a situation where they might say the obtuse angle this or the reflex angle, or they might say the acute angle and the reflex angle. So suppose I'm going to make this a bit larger here. So this is A, B, C. And we have here this angle, which we'll call 40 degrees. And you might have the reflex angle all the way around, which would be 320 degrees. So in this case, they would classify this as the acute angle, CBA. Or if you don't want to call it CBA, you could call it ABC. That's fine as well. I do prefer to write in the same color though. So this would be 40 degrees. And then they would go out of their way to label this the reflex angle. A, B, C, which would be 320 degrees. So this is how you could differentiate which one's which. They'll have to tell you, or you'll have to tell us, that it's an acute angle that you're talking about, or it's the reflex angle that you're talking about. Okay. And again, it's worth noting that if you have angle A, perhaps we should write this one in our darker color here. If you have angle ABC, that's the same thing as angle CBA. Typically, it doesn't matter too much how you orientate it, but usually we read from left to right, so as best as you can in your diagram. Okay, and that's what they tried to do here as well, right? They kind of started on the left and tried to make it work, but again, it's pretty loose. The angle that you care that the angle that forms what we're talking about will be B. Okay, so let's continue on. So here we have a whole list of properties that we're going to be talking about. So we have we have a whole list here: circle, chord, arc, segment, tangent, secant, sector, central angle, and the inscribed angle. And then we also have a matching section afterwards that we're going to try out. And so we're going to go through these one at a time and just describe these as best we can. Okay, so a circle is a set of points that are a fixed distance, the radius from a given point, the center of the circle. A more eloquent way of saying this might be a set of points all equidistant from the center. Is another way to describe this. Okay, so that's just basic circle. A chord, so pronounced chord without the H, is a line segment inside of a circle that joins 2 points on the circumference of the circle. Okay, so you can see here in our diagram, this line corresponds to our chord. Now, if these 2 points inside of the circle happen to go through the middle of the circle, that has a special name, which you know. We call that the diameter. So the diameter is a chord that passes through the center of a circle. So all diameters are chords, but not all chords are diameters. So there you go. An arc is a portion of the circle that joins 2 points on the circle. So the smaller arc is called the minor arc. The larger one is called the major arc. Okay, so here you have a circle, and if we zoom in for a moment, we can see that, say we'll put the point A here. Oh, I'm all very zoomed in, aren't I? Okay, zoom out. So say that we call this A, B, and C. We can see that here, this is the arc that contains the point C. This would be the minor arc. If we had a point on the opposite side, say point D, and we were interested in that particular arc, remember, you should be thinking of, this kind of reminds me of how many radiuses are on the circle. It's kind of the same area, except same domain, but we're talking about just we're going to be working in degrees. This is what we call the major arc. Okay. We don't often differentiate between those, but just know that it does have a name. And for this lesson, we will make sure to describe this. And so we end up with something called a segment, however, is a part of a circle bounded by a chord and an arc. So here, the shaded area is what we call a segment. And we're actually going to learn how to determine the area of such segments in the lesson of next time. Okay, so you can write the segment. So all you do is have a chord, and then you have the arc, and then you shade in that area, and that's the segment that we care about. Okay. A tangent is a tangent to a circle is a line segment. Well, it should be just a line that intersects the circle at one point. So here we have our tangent. You can see it just touches the circle at one point. A secant to a circle is a line segment that intersects the circle at 2 points. And again, we should say a line, but sometimes the textbook gets things wrong. There you go. And so that's a secant. And the secant can be orientated however you would like. A sector is the area enclosed by 2 radii of a circle and the arc that connects the endpoints of the radii. So all this means is, if you were to sketch out what this looks like, if you were to take your 2 radiuses and move them out to a given point, that would be this, and enclose that area, that would be a sector. So here's our circle, and the sector might be this. Now you could have a sector the other way, in which case you would have to differentiate that and call that the reflex angle. So you know how earlier up here we talked about the reflex and the obtuse angle? This is what we're talking about. So there is the obtuse angle of the arc. So say this was A, B, and C. So we could have the sector with minor arc, A, B, C, or you could have the sector with major arc, A, B, C. And again, in this case, I think the minor arc would be the obtuse angle, and the major arc would be a reflex angle, if you needed to further clarify what we're talking about here. Okay. The central angle is the angle that is formed. Okay, so we saw that in the when we studied radians as well. And lastly, we have something called an inscribed angle, is an angle in a circle with its vertex on the circle itself. So it doesn't use the radius at all. So just that's what we call an inscribed angle. Okay, so let's put that knowledge to the test. We're now going to match each term with the correct diagram to be able to tell what is what. And so the only thing I'm going to do is I'm just going to label this 1, 2, 3, 4, 5, 6, 7, 8. The textbook I took this from used the Roman numerals, but I don't have enough space to write that, so we'll just go ahead and rewrite this. Okay, so we got to match these up. So you don't need to go in order for these kind of things, just be able to identify what these are. And so the easiest one to identify is the one we just did, the inscribed angle. That's clearly number 6 here. So the angle is on the outside of the circle. And the reason for that is if you have a look at number 1 here, we have a circle given by AOB. We're not exactly sure what that represents. We're not sure if that represents an arc or maybe that represents the central angle. It's not clear immediately, so we'll leave that one till last. And so my recommendation is to do all the ones that are much more obvious. So for example, the segment or the sector seems reasonable. Maybe secants and tangents are also reasonable to tell. So let's have a look through that. So number 5 then, that's definitely a sector, since we can see it's a shaded pie slice. 7 was the segment because it was, if we connected A and B together and then found the area of that segment, that's what that would be. So we'll call that one here. Number 8 looks like a tangent. So it touches one point on the circle. So there it is. The secant, oh, looks like this one here. And so we connect the lines as such. That's why I had to go correct my notes from up there, because if you notice from our diagram here, if we connect AB with just a line, that's a segment. If we extend the line through AB, that's a secant. And so that should give you a hint then that AB, for number 2 here, if we're connecting 2 points inside the circle, that appears to be a chord. So now we've got 2 options left. Number 4, we have point O, and then we have A, B, and some point C on the arc. So that appears to be an arc, which means that number 1, which was the most difficult to tell, happened to be our central angle. So we just left that one till last. Okay. Okay, we're going to identify some more property circles. So now this is a support question I took from the textbook that seems like it'd be a good one to go through. In the diagram shown right, O is the center of this particular circle, and we just have to label what these are called. So what would O to B be called? Well, OB appears to be some kind of radius, so we'll just call it a radius. What about BC? Well, B to C, we're connecting 2 points on the outside of the circle with a line segment, so we will call that a chord. What about for CO? Well, that looks like another radius. What about B to D? So B to D is a chord, but it goes through the center of this. It goes through the center of the circle. And so that's what we call a diameter. What about CDB? Okay. So if we go C to D to B, like that. So that means we're going all the way around the circle. So that is an arc, but it's worth noting that that's the major arc. If we had talked about, say, CBD, if we had, say, another point on this side, that would be another arc as well, but that would be the minor arc. So CDB all the way around, that's called a major arc. What about angle BOC? So if we want the angle from, let's put this in red, BOC. Oh, so we see that's an angle carved along point O. And if you're not sure, you can use the diagram from above to help you. But this is what we call the central angle. What kind of triangle is OBC? So if we have a look at this, what kind of triangle is that? Well, we know that OB is a radius R, OC is a radius R, which means that this is going to be an isosceles triangle. Oh, maybe I should write out the word triangle. Okay. If angle B is 65 degrees, so they're saying that this here is 65, what is the degree measure of BOC? So they want to know what this theta value is. Well, if we know that this is isosceles, BCO will be 65 degrees. CBO will be 65 degrees, and then theta will be the leftover angle. So theta will be equal to 180 minus, and in this case, since they told us specifically angle BOC, we should label it as such. So angle BOC will be equal to 180 minus 65 degrees minus 65 degrees. So angle BOC will be equal to, so if we take 180 minus 65 minus 65, we get angle BOC is 50 degrees. Okay, so this is how we're able to identify different characteristics and parts of this circle. Okay, so example 5, we're going to actually sketch what these things look like. So we're going to sketch a circle that satisfies the following conditions, and it just has various things for us to worry about. Okay, so let's have a look. So for example A, we need a diameter. Okay, so we'll draw the middle of the circle. So this will be our diameter. We'll put in this color. I should probably just write out the word. We need an arc. Okay, so here we'll go A, B, and a point C. So this is the arc we care about. And we need a secant. So secant was just, we could extend the diameter, but we'll just draw 2 points instead. And perhaps we'll space these out a bit more. So secant, remember, is just a line passing through any 2 points on the diagram. Oh, that's pretty good. There it is. So there is our secant. And we labeled the corresponding colors as well. And so I should also mention for this one, your answers will vary. So you don't need to produce exactly this diagram. You could have also wrote it, like say, for example, you could have like dotted in these lines, like included 2 radiuses and then said this part of it was an arc, and that would be okay as well. Just the diameter could have been orientated however you want, and so could have the secant. So there's lots of answers that this could have been. Okay. Letter B, we need a tangent, a central angle, and a sector. Okay. So let's do that. So let's draw out the center of the circle. So we need a sector. So that's like a pie slice. So here, in this will be the central angle. So I tried to avoid drawing the angle up in there because otherwise that would include the central angle, even though we're going to find out in the lesson of next time that the arc will involve the central angle as well, but that's okay. So there is our central angle. The sector is going to be the area of the inside of that pie slice. So let's go ahead and color this in red. It's very satisfying to color this in like this, by the way. Very good. So here, this pie slice will be our sector. And again, the sector could have been larger or smaller. I just made it this size so it's easier to read. And we'll go ahead and label the sector in red. And then the tangent touches the circle at 1 point. So we'll label this the tangent as so. Okay, last thing we need is a one with an inscribed angle and a segment. So and if you don't remember the inscribed angle, that was the one where the angle was sitting on the circle itself, extended to 2 outside points. So we saw that diagram from above, so why not replicate it? So here's our inscribed angle. So let's pick 2 points like such, or 3 points total on the circle. So we'll call this A, B, and C. And here is the inscribed angle theta. So we would say that angle ACB is the inscribed angle. Okay, what about the segment? So the segment would be, we connect two of these points, and then we would shade this in. Very good. And so we'll label this. This part here is a segment. And again, we can actually figure out if we had the center of a circle, and it's worth noting this now, the segment is a subsection of a sector, right? So if we have a look at our diagram from above, if you notice for number 7 here, this entire the area enclosed by A and B on the arc side, that's the segment. But if we were to color in this entire thing, oh, that would ended up much bigger than I thought it was going to be. Perhaps we'll just do this in red instead. If we were to enclose this entire area, that would the entire thing would be the sector. We're going to see in tomorrow's lesson where we will talk about how to determine the area of the segment. It actually involves a sine theta, so that'll be fun for us. And that's how we're able to do this. So here, this is how we're able to sketch these various shapes and anything that we're interested in. And so an application of this kind of information can actually be extended to 3 dimensions. So I just picked this question just as something you've likely never seen before, and is just a random thing that you're able to do involving these kind of properties, and that they extend to higher dimensions. Higher dimensions being, instead of a circle in 2 dimensions, can we talk about these things in 3 dimensions? And the answer is yes. So we end up with something called a spherical cap, and this is the region of a sphere that lies above a given plane. So instead of the case of a segment where we connected 2 points and we talked about the shaded area enclosed by those 2 points. Oh, let's just try drawing that one again. Okay, so there was our segment. A circle is the 3-dimensional version of this. So if I were to and trying to sketch this out, but I don't think it's going to go well. All right. Actually, that turned out okay. So the spherical cap is the 3-dimensional version of the segment. Okay. In general, the volume of a spherical cap is given by the formula, and we have this 1/3 pi r squared multiplied by 3r minus h. Reasonable question. R is the radius. Okay, we can see in our diagram here. Let's work in this color. R equals the radius, and h equals the height of the spherical cap. Note that you can also do this with angles. It's just a little bit different, a different way to describe it, but we're going to stick with this. We're determining the volume of a spherical cap with height 20 centimeters in a sphere of 40 centimeters. Okay, so important caveats. Here we were told the radius is 40, so r is equal to 40 centimeters, and this height is going to be equal to 20 centimeters. So using the formula, V volume of a cap is equal to 1/3 pi squared times 3r minus h. Again, you might be thinking pi squared, just has to do with the formula. We know that pi is equal to 3.14, r is equal to 40, and h is equal to 20. So this volume will be equal to 1 divided by 3 times 3.14 squared multiplied by 3 times 40 minus 20. And so we've seen these kind of calculations already with surface area of various shapes, but why not try out this one? So the volume of this cap will be equal to 1/3. Oh, we could just write our answer directly. So let's type in 1/3 multiplied by 3.14 squared multiplied by 3 times 40 minus 20. So this volume is going to be equal to 328.653 repeating, which we'll call 328.65. And since we're talking about units, since we're talking about volume, we have to write this as centimeters cubed. I was going to write units cubed, but then I saw they actually gave us the height in centimeters. Okay. So here, this lesson helped us to identify various characteristics of a circle with one application to say that this does actually continue up into higher dimensions as well. And so here, if you're able, as long as you're able to kind of tell the difference between the various properties of a circle and be able to label their corresponding characteristics and properties, you should be okay. So I think that's a good place to stop for today. Tomorrow, we're going to have a look at calculating areas of sectors and segments and actually figuring out the length of the arc. So that's a good place to stop. If you have any questions, please feel free to reach out, and I'll see all of you next time. Goodbye for now.